Hello, my students. Are you ready for lesson 57? The topic is ideal gas laws. That sounds hard, but it's not. Ideal gas chemistry, and if and when you take chemistry, you will bump into these and you will feel so smart because you already know a little something about them and you know how to handle the math in them. So, yay for being prepared. In ideal gas laws, okay, ideal gases are a certain kind of gas, right? You know, gas, liquids, and solids. So they're gases, and what's cool about them is that they maintain an equilibrium. There are three different components. There's the pressure, and there's the volume, and there's the temperature. All those things can be measured about gases. And what's cool is that if you change any one of those, the other components will balance out so that whatever the first balance was, the second one will be equal to it. This is the formula that we need to use, and I'm just going to write this down. P equals pressure, V equals volume, T equals temperature. I'm not going to spend too much time talking about those because that falls more under the science heading of this lesson, temperature. But what I want you to do is look on page 245 and you will see some bullet points. And what John is giving you is different units of measure for pressure, for volume, and for temperature. There are different ways those things can be measured, and the reason it's helpful to know that is because when we read the problems, we might be given those specific units, and John will help you out. He'll make it easy. But if you want to know what the heck is, kelvins. What are kelvins? What does that measure? Does that measure pressure, volume, or temperature? If you look at that list on page 245, you'll go, oh, kelvins are temperature, so that's where that number goes. Like I said, John makes it fairly easy to figure out, but this is a good resource for you on page 245. This is the formula you'll need to know to work these problems. The math at first is going to be simple and clean. There's nothing to be afraid of. Okay. Example 57.1. 4 liters of an ideal gas with a temperature of 800 kelvins had a pressure of 100 newtons per square inch. Oh, goodness, that sounds so hard, doesn't it? All right, let's break it down. 4 liters. All right, I go back to page 245, and I look on the list, and I look for the word liters. Oh, I see it under volume. So that tells me that the first volume is 4, okay? Then it says that the 4 liters are at a temperature of 800 kelvins. Okay, the first temperature is 800. I'm not worrying about the units. I'm not going to write that down. I'm just writing down the numbers. And it had a pressure of 100 newtons per square meter. Cool. Okay. If the volume were increased to 10 liters, okay, so that means our second volume is 10, and the temperature is reduced to 600 kelvins, so the new temperature is 600, what would the pressure be? Okay, so P2 is the mystery. All right, so as our formula kind of hints, this is one of those kinds of problems where we have an initial situation and then a change situation, and the formula shows us that they're going to be equal to each other. So we can just fill this in. I'm going to write buckets. Oh, my little buckets are squished. My second set of buckets. Okay, so this represents that. I'm going to fill in numbers. So I'm looking for the first pressure, 100. The first volume is 4, and the temperature goes in the denominator, that's 800. Okay, so this is my first setting. And now my second setting, let's see, and here goes pressure. Okay, that's the mystery. So I'm going to put just a P in there. The second spot is volume, so that's 10. And then the temperature on the bottom is now 600. All right? Okay, cool. So now we've got it all set up. All we have to do is algebra the heck out of it. So what I'm going to do, and so I'm going to multiply this by the reciprocal of these two. So I'm going to multiply this by 600 over 10. I'll write the 600 up here and the 10 down here, and then over here I'm going to write it a little bit differently. 600 over 10. Okay? So now my 600s cancel, my 10s cancel, my p's by itself, and all I have to do to finish this is simplify this big clump of numbers. So that's what I'm going to work on. The first thing I'm going to do is cross off matching sets of zeros. I can do that, for example here, I'm going to cross off 2 zeros and 2 zeros. What I've done is I've divided top and bottom by 1. Perfectly fair. Now I'm going to cross off this 0 and this 0. I've divided top and bottom by 10. Okay, so I'm good. Now I'm going to write what I've got left. I've got 60 times 4, that, this is all gone, this is all gone, that's just a 1 left, and now I'm over 8. Okay, so now I can keep canceling. There's a 1 and a 2, and now I've got 60 over 2, and that is 30, and so my final answer is 30 equals P2. So that means my ending pressure is 30, whatever the heck we're measuring it in, and I don't even care if you write the unit because it's so far gone, but I'll just look and see what it is. The pressure is measured in newtons per square meter. Newtons per square meter. That is a unit that means absolutely 0 in my brain, but it's fine. I can write it down. Okay? Let's try another example. There are 3 total in this lesson. Okay, example 57.2. My previous page, so let's write it over. P1, V1, T1 equals P2, V2, T2. Puffy cloud of knowledge to surround that lovely formula. And I know I'm going to need these, aren't I? Oops, V2. I like to keep them in order so that when I go to fill in my formulas, everything's right in the order that I want it. One of these will probably be a mystery, but that's okay, we'll figure that out. Okay, the initial pressure of a quantity of an ideal gas was 400 newtons per square meter. Okay, so pressure 400, that's what I took out of that sentence. And the initial temperature was 1,200 kelvins. The volume was held constant. Okay, so that means the two volumes are the same. They don't change. John hasn't told us what the volume is, but he tells us that it's unchanged. What was the pressure of if the temperature was decreased to 900 kelvins? So what was the pressure if the temperature was decreased to 900 kelvins? Okay, so we look at our chart of numbers and we go, wait a minute, we don't have the volume. How are we going to do this? Drama in the hood. But there's really good news, you guys. If the volume is unchanged, we can drop it out of the formula. So we're going to adjust our formula to just be P1 over T1 equals P2 over T2. So if any one of the three factors is unchanged, you can just drop it out of the formula and write a simplified version, and then we'll just use those numbers. So look, it's going to be so easy. P1 is 400, T1 is 1200, P2 we don't know, and T2 is 900. Come on, that's great. So I could cross multiply, but then I'd have to do dividing. So what I'm going to do is I'm going to multiply this side by 900 over 1. That's the reciprocal of this, right? Those will cancel. This will be fine. And so I have to do the same over here. 900, and I'll put the 1 there, but that's not really even necessary, is it? So these are equal. These cancel. P is by itself. Now I just simplify on this side. The zeros and the zeros, I just divided both sides by 100. And now let's see, what can I do here? The 4 and the 12, I can make that 3, and that would become a 1. And now this cancels too. 900 over 3 is 300 equals P2. Yay, that's the right answer. Our previous one was correct too. I don't think I said that. So that newtons per square meter is what we're measuring in again. Yay! We did it right. So that's the magic lesson of the second example, is that if any one of the three variables is unchanged, that means you can drop it out of the formula and just use a simplified version. Hot diggity. Let's flip and do the last example for this lesson, example 57.3. I still don't have the formula in front of me. I keep changing the page. That's okay. It'll make me memorize it. Please write this down wherever it is that you write down your formulas. Inside cover of your notebook is my favorite place. V1, T1, P2, V2, T2. Okay, let's read. The temperature of a quantity of ideal gas was held constant in an experiment. Okay, so temperature stays the same. Yay, we get to drop it. Cool. The original pressure was 7 atmospheres, whatever that means, and the original volume was 42 liters. If the volume was reduced to 10 liters, what was the final pressure? Okay? So again, we're ignoring the temperature, don't even care, it's the same, so it doesn't affect anything, so we can drop it out of the equation. In all three of these problems, I just noticed, we're solving for pressure every time. That's just a fluke. It doesn't matter which of the variables we solve for. It's not harder or easier to solve for a different one. That's just the way these problems turned out. So don't let that throw you at all if next time they ask you for temperature or volume. It's no harder, it's just different letters. Okay, so I'm going to adjust our formula because we don't have temperature. So it's going to be P1V1 equals P2V2. By temperature, bucket it up. P1 is 7, V1 is 42, P2 is what we're looking for, and V2 is 10. Yay. So all we have to do is divide both sides by 10. This cancels, P is by itself, and now this, we could cancel this against this, but it might be easier to multiply this and then move the decimal once as our division by 10. So we're going to try that approach. Scientists love decimals. Mathematicians tend to prefer fractions, but scientists love decimals. So we're going to give this nice little science problem a decimal answer. So I'm going to do 42 times 7. 7 times 2 is 14. 7 times 4 is 28, plus 1 is 29. And then to divide it by 10, I'm just going to bump that in. So the second pressure equals 29.4 atmospheres. Don't know what those are. That's okay. I just read it out of the problem. And that's the right answer. Don't let this mess you up at all. Just know that as soon as I saw that fraction with a 10 on the bottom, I thought lovely way to give John, who's got his scientist hat on, let's give him a decimal answer, because that will be happiness for scientists. If you gave me a fractional answer, if you gave me, we multiplied these, we got 294. If you gave me 294 over 10 and then reduced it to whatever that would be, let's see, this would be 147, is that right? Over 5. Let's make sure 147 and 147 equal 294. I don't trust my brain right now. Yes. If you gave me this as an answer, I would say yay, also beautiful. If you looked in the answer, the solutions manual, you would find this answer and you would have to figure out how to get from there to there, but that's not hard. So anyway, either way that you like to do that is just fine with me, but John's answers in decimal format, so you might as well play the game. That's it. That's all there is to lesson 57. Those ideal gas laws are nowhere near as scary as we thought.